Great. All right, so I would like to introduce Vincenzo Nicosia, or Enzo Nicosia. He received his PhD from the University of Catania. He's co-authored a textbook on complex networks from Cambridge University in 2017. He currently sits in the editorial board of the journal Complex Networks, Complexity, and +1. He's done a lot of work in this field of network science, which some of you might be aware of and some of you would like to know more about. And he specifically sort of blends a little bit of network science with computer science by looking at the structural properties of networks, including multiplex networks, and the characteristics of dynamical processes occurring on these networks. Today, he's going to specifically talk about the algorithmic complexity of complex networks. And with that, please take it away.
Cool. Thank you very much. Thank you very much for the invitation, and I hope we will be able to keep this as informal as possible, as I was saying to Keith. So please, if you have any question at any point, just stop me or write in the chat, because I should be able to see the chat.
And if I may interrupt just very briefly, I also wanted to emphasize that the next, while he can talk from 11 to 12, there's in fact an additional hour from 12 to 1 p.m. Pacific time, when he'll be able to do an open Q&A at the very same link here. So don't feel pressured to stop your questions and answers. We'll be here for a while.
Yeah, exactly. But don't be afraid to stop me either way, because again, if it's interactive, it's going to be better. It looks like I can't see your messages, so just open your mic if you have a question.
How about I'll share messages as they come up.
Yep. Cute. Yeah. Okay. Let's do like that. Yeah. Great. Okay. Should I start then? Great. So this talk is going to be about algorithmic complexity of multiplex networks, and I think the reason why I'm here is because we had some email exchange with Keith a few months ago when one of these two papers went out about whether there is whether it makes sense to define a algorithmic complexity for multiplex networks, and whether the way we actually choose to define algorithmic complexity for multiplex networks makes sense at all. So I was very happy to receive this invitation from Keith, and I think we can. I hope we can actually have a discussion about this stuff if you like. Okay, so what are we talking about? We are talking about complex systems. And the thing is, if you actually ask 1,000 people what is a complex system, you would probably receive something like 3,000 or 4,000 different answers from them. So it's something that has been around for a while. I mean, there are several definitions of what a complex system is supposed to be, or what is a complex system, or where a system is considered complex. But I mean, again, there is not that much agreement about these definitions. So I like to use a definition that is from a friend who is now in UCLA. Be careful if there is anybody under the age of 18, they should leave now, because the next slide contains strong language. And the definition is as follows: complexity is like porn. You can't actually define it exactly, but when you see it, you know. And this is by Mason Porter in UCLA. I like this definition very much, because it says it all about how hard it is to actually define complexity and what it is, what a complex system is. So let's get back to our question. For me, a system is complex if it consists of more than one unit, and in general many units. If each unit has some sort of dynamics, and the dynamics doesn't have to be particularly complex on itself, it could be even a simple dynamics. But more importantly, this system should allow for non-trivial interactions among its units. So if you have these three components, I think that I would have no problems define your system a complex system. But the reason why such a system, so a combination of units, their dynamics, and the interaction between these units is complex, is that most of the times this kind of complex systems give rise to interesting behaviors, which, for instance, cooperation, synchronization, spreading, and so on, which cannot easily be attributed to just the single units, just the single dynamics, just the interactions. So the combination of these three ingredients normally is responsible for the emergence of these interesting behaviors. When I say interesting, I mean something that is not trivial, something that you couldn't really expect from the observation of the microscopic elements of your system. And there is there are different takes on complex systems, but the hypothesis of complex network theory is that if you have a complex system and you just look at the interactions among the units of your system, you can still recover most of the interesting information about the working of your, or the functioning of your system. And so there's been a long, a long wave of literature on studying complex networks in this sense, and tying up the complexity of the system with the complexity of the structures, the complexity of the scaffolding of the interaction network among its units. But there are other more recent developments, let's say, and one of these is the multiplex network metaphor, which is basically along the same lines of classical network science, with the difference that in a multiplex metaphor, you normally look at each interaction and try to disentangle all the possible ways in which two entities of your systems, which are represented as nodes, can be connected, can actually be interacting. And this is not that far-fetched as an hypothesis, because if you think about it, we have thousands of multi-level or multi-dimensional systems around us. The basic example is that of human societies, where the units are obviously people, and they can interact in several different ways. They can befriend. Can you see my pointer by any way? Can you see my pointer? No.
No, I don't believe so.
I don't think so.
Okay, so I'll take care of that. So it could be that the interaction between two people could be friendship, could be Facebook friendship, could be familiar interaction, could be economic, financial relationships, could be co-location if you go somewhere and have a beer with your friends. It could be collaboration. It could be communication, other old way communication, or the several thousand different ways in which today we can communicate. So this is an inherently multidimensional system. So a system where the connection between two people is not simply a link, but is something that is much more rich, much richer than just a link. And then you have another paradigmatic example, is that of multi-level transportation systems. In a large city, in a large metropolitan area, you normally have different ways of getting from one point to another. And this is a rich, very rich system, which exhibit very rich dynamics, obviously. So just connecting two places in London by a link without saying whether this connection is done by car, by train, by bus, or by tube, it's losing a lot of information. So the multiplex metaphor consists into representing these multifaceted information with a multi-layer graph. So you basically have one layer for each kind of interaction, and you record all the different interaction of one type among all the nodes you have in your system, and you put them in one layer. And for another kind of interaction, friendship, you get all the interaction of type friendship, and you put them in another layer, and so on and so forth. And the idea here is that the nodes are identified across layers. So node one is the same person in different layers, but the edges to other nodes depend on the kind of interaction we are actually taking into account. The same is for the transportation, the example of the transportation system, where each mode of transport is mapped into a different layer. Now, Obviously, this has been made possible by the availability of multidimensional data. So the more data we have, in principle, the happier we should be. Um, well, that is more or less the picture. So if when you have a complex system and you use the traditional network lens, you're just focusing on the network of interaction among the units. If you use what I've been calling the multiplex prism, which is not anymore a lens, you get a multifaceted representation of your system. So you're just taking into account of all the possible ways in which the nodes could be interacting. But there are problems with when you have too much data. And now I'm not talking about information anymore, but about data. So we have plenty of data sets which record the multiple ways in which a set of units can interact. But we want to understand whether we actually need all these data. So whether these representation of your system, which consists of taking one layer, one different graph for each possible kind of interaction you have among the units of your system, whether this representation is actually useful, or whether there are instead smaller number of layers, representation with a small number of layers, which can provide the same amount of information. Well, I think this shouldn't be too much of a surprise in a an information science context, but there are still many many shops where this concept is not that familiar. So we have been working a bit on this problem, and the first stuff that we did was what we call the multiplex mincer machine, um, which which is exactly what it says. So it's a small machine that works like a mincer. So you provide a multiplex in, and you get a somehow minimal multiplex network out. So it's a machine that basically quantifies the information content carried by each layer, estimates the difference between layers, merges similar layers in the single one, and hopefully will find the best representation of your system, which is the least redundant, minimal, and preserves as much information as possible about the original complex system you're interested in. How it does that? Well, to compute the layer information content, we use a some information that can be easily extracted from a graph. And in particular, we consider the so-called rescale Laplacian. This is just a matrix associated to the graph, which depends on the adjacency matrix. This A here is the adjacency matrix, and D is the diagonal of degrees, and 2k is twice the number of edges you have in your graph. And it turns out that a synthetic quantity that represents this information in some sort of coherent way is the entropy of this matrix, which is normally called the von Neumann entropy of your graph. We will understand in a minute why this is called von Neumann entropy of a graph. And then to compute the distance between two layers, in principle, we could use the same formalism. So we could consider the two layers on their own. We could consider the combination of the two layers. So they some sort of sum, however you define it. And then we can compute the Jensen-Shannon divergence between the two layers, which is the difference between the von Neumann entropy of the mixture minus the average entropy of the two layers. If the two layers are identical, then this distance will be this divergence will be zero. If this divergence is larger than zero, then it means that your layers differ by a certain amount. Why this stuff works? Well, this works just because of a purely formal relation between graphs and quantum states. So all this formalism comes from quantum information theory. And the thing goes like that. So in a graph, you have your Laplacian, which is just that operator, that the rescaled operator I talked about before. And the good thing of this Laplacian, it's that it has a unitary trace. So the trace of the Laplacian, so the sum of the elements in the diagonal is equal to 1. And this Laplacian is identically functionally formally identical to the density operator of a quantum system, which is an operator that has exactly the same properties of the Laplacian, so it's positive, semi-definite, and trace 1. And in the case of quantum states, this operator measures the extent to which the elementary state of your quantum systems are mixed. So if you have just a pure state, a pure quantum state, the von Neumann entropy of this operator will be 0. If you have the combination of states which are more entangled, then you have a von Neumann entropy that is larger than 0. So the idea is that this can represent how much intertwined are the elementary elements of your elementary states of your graph. We can get back to that. It's a technical issue, but we can back to that if you want. And the parallel goes on, because if you have two different quantum states, rho 1 and rho 2, then the distance or the difference between the mixedness of the two states is measured by the Jensen-Shannon divergence between the two operators. And this is why we decided to use the Jensen-Shannon divergence as a way to measure the difference between two graphs. So the Jensen-Shannon divergence of the corresponding Laplace operators. So this is the formal mathematically, if you want, parallelism between quantum states and graphs, which allows to use these quantum information theory principles to quantify to some extent the information contained in a graph and the difference between two graphs. Then if you want to merge similar layers, what you do something pretty standard. You just find the pairs of layers which provide the largest Jensen-Shannon divergence, meaning that they are the layers that are most similar among the set that you currently have. And in this case, it's L1 and L3, for instance, and then you just go to a multiplex that has a multilayer system that has one layer less, in which you have basically aggregated the two layers which provide the best, the smallest increase in Jensen-Shannon divergence. So in order to merge similar layers, we use the usual representation. So the dendrogram representation, a node represents the aggregation of groups of layers, and you want to cut this dendrogram at some point to get a best configuration. The problem is that whenever you have a dendrogram, you need a quality function to decide where to cut. So what is the best representation of your system? It turns out that quantum information theory can help here as well, and provides us with a natural, in terms of quantum information theory, a natural way of defining a quality function for this stuff. And in theory, you would like to have a representation of your system that has minimal information loss with respect to the original data sets, the original m-dimensional data set we used, and maximal information gain with respect to the representation that just flattens all the data set in a single graph. So we would like to find these trade-off, the best to optimize these trade-off. How do we do that? So if you have a multiplex with m layers, in principle, you can compute the von Neumann entropy of these multiplex. An upper bound for the von Neumann entropy of these multiplex, which is just a sum of the von Neumann entropies of all the graphs you have of all the layers you have in your system. But what you could do also is to compute the von Neumann entropy of the aggregated graph that you would obtain by flattening all the layers in just one network. And these are the two extremes we were talking about before. So on one side, you have the von Neumann entropy of the system where all the layers are kept separate, which is the initial data set. And on the other side, you have the aggregated graph, which represent the dumbest, if you want, way of using that information. So flattening all the information in a single graph. And what we do is that if we have a configuration with less than m layers, we can compute this quantity here, which is a relative entropy. So it's 1 minus the fraction, the ratio between the von Neumann entropy of your system with x layers, with k layers, and the von Neumann entropy of your system with of the aggregate system. And this is a relative entropy, but in quantum information theory is also a quantity that is related with the amount of information you can extract from a quantum system with just one measurement. And it's called the whole-level information or whole-level quantity in quantum information theory. So this formalism provides us also with an easy way of quantifying the best partition. And so the maximum, the aggregated system for which we have the maximum information gain with respect to the aggregated graph is the one that has the maximum value of these O-level quantity. We use this stuff to analyze the extent to which different systems, different multi-layer systems could be flattened, reduced in a smaller dimensional graph. But there are a few issues with this von Neumann entropy, although, I mean, the method that has been used far and wide, farther and wider than we actually expected at the beginning. There are a few obvious issues with this method. The first one is that the parallelism on which the method is based, so the duality between quantum states and graphs is merely formal. So we can't really say that graphs are quantum systems, and we never claimed that, to be honest with you. But we just use the cool property that some operators associated to graphs can actually happen to have the same useful properties of some other operators associated to quantum states. So this parallelism is merely and primarily formal, not substantial. And then we also have the problem that this von Neumann entropy doesn't have an immediately intuitive interpretation. So when we actually flatten two graphs, two layers, it's not easy to understand or to explain why these two layers should be flattened instead rather than not. And in particular, we did a large series of experiments where we considered one layer and the same layer with some defects, and a variation in von Neumann entropy of this very small, simple experiment were too large, or if you want, which is a catchphrase in the last few days, too close to call. So you couldn't really tell the difference between configurations that were very far apart, or distinguish comfortably configuration that were too much similar. So there are some issues there, although the system, this formalism seems to be working well because it provides intuitively good results. But when we want to explain why, that's totally different story. Okay, if you don't have any questions so far, we'll keep going.
Sorry, can I ask a quick clarification
Sure.
question?
Go on. Yep.
So let's say you have a two-plex network, and let's say you are interested in a simple microscopic characteristics, like whether it's below or above percolation threshold.
Yeah.
So I can envision a scenario where in each layer the system is below percolation threshold, but collectively two layers are, above. So this seems to be a very, big quantitative change, and I'm surprised that you can capture that by doing that, simple.
And in fact, we can't capture that, and this is the reason why I will be talking about another formalism in a couple of slides, which instead seems to be able to capture these differences. So the main thing is that with these phenomenon entropy formulas, you cannot always distinguish or detect the formation of artifacts in your system. And an artifact could be they change in the percolation threshold, for instance, right? Or an artifact could be they change in the number of triangles you have in your system while you flatten. So you could have, you could start from layers that have no triangles at all, and you could end up to a system by flattening and flattening. You could end up in a system that has a considerable amount of clustering. But obviously, this clustering is always an artifact, so it's not the real thing that you had in the original system. It looks like this measure, this phenomenon entropy, is not able to explain why a certain flattening is good, and it doesn't always guarantee that the flattening is not creating artifacts. Does it make sense?
Yeah.
So your question makes a lot of sense, and apparently this measure is not able to do that. Okay. But what I will talk about in just 2 slides should probably solve the problem. Any other questions so far?
Yeah, anyone is feel free to ask a question or to raise their hand using the button on the right.
So, Anson, I don't know if this is exactly the right, point in time to ask this question, but since we, broke. So how does this compare to all the sort of like multiplex graph, or not even multiplex necessarily, any graph compression technique that is based on things like, the info map, the map equation, and so on, that's kind of like entropy-based compression?
Okay, so if you talk about multilayer graphs, actually, the difference is that this came much before those, because this is a work from 2014, and then most of the map equation related stuff is from later than that. Mm-hmm. And I've also discussed it with Martin Roswell, and we are actually currently working a bit on some generalization of the map equation for this kind of stuff. And indeed, the main issue I see is that the map equation can mix pieces of layers instead of entire layers, which makes the interpretation even hard. So I think a good aspect of the phenomenon entropy is that it is a clear-cut, even if simple, a clear-cut procedure. Either you flatten 2 layers or you don't. In the case of InfoMap, you can have all sorts of middle ground. So you can just cluster together pieces of one layer with pieces of another layer and get something else that is not anymore a multiplex or a multiplex or a multi-layer network in the same class of the original system. So they have different, different scopes. But definitely, I think the main difference is that this came 1 or 2 years before the InfoMap procedure. So we couldn't actually compare with that.
Gotcha. Thank you.
Okay. Anything else?
No, it appears not. No questions in the chat either.
Okay, let's move on then. So one thing that is very hard to do with phenomenon entropy is actually to compare 2 different multiplex networks. So imagine that you have these 2 systems. So the system on the left is a system that has 3 identical layers. So it's in theory a multiplex network, but in practice it's just a single layer network where I have repeated the same layer 3 times. While the system on the right is a truly multiplex graph. Now I want to ask you which one of the 2 is more complex, where without doubt you would say that the system on the left is simpler in a way, or less complex than the system on the right, just because the same layer repeated 3 times is not really adding any more information to the single layer system you could consider. While the system on the right it should be considered a bit more complex, just because you have several different dimensions where information could be added in terms of structural information could be added. Okay, so there wouldn't be no doubt possibly about the fact that the system on the right is inherently more complex. But what happens if now I have two systems like that. So on the left, I have the system I previously had on the right. And on the right, I have another system with 3 layers, which provides me with a different arrangement of links among the different sets of units. How do I compare the complexity of these two objects? The problem for Neumann entropy is that it could easily give you the same number for two systems like that, even if they have no intrinsic relation in terms of how much complex they are. So deciding which of these two is more complex than the other is a bit more difficult and less intuitive overall. So it would be very difficult to disentangle these with normal, with the usual multiplex network approaches. And at this point, I would question which kind of complexity are we talking about, because I told you that a system, according to my judgment, is complex if it has an interesting structure and can give rise to interesting behaviors. But here it seems that we are talking about how much potential information is included in your system, in the system on the right and in the system on the left. Okay, let's cut it through. And basically, we know that in information theory, one possible way of defining complexity is in terms of description length. So if an object is simple, then it could be is not complex, but then it could be described with a simple description. If it's more complex, then it normally requires a description that is longer or more convoluted. And there is one particular case of description length-based complexity, which I always found quite appealing, and this is the definition of Kolmogorov complexity. I know that some eyebrows will raise right now, but bear with me, and then we can fight later on. So what is the Kolmogorov complexity? Kolmogorov complexity is the Kolmogorov complexity of an object is the length of the smallest computer program, or better, the smallest program for a Turing machine that can generate it as output. So if you want, Kolmogorov complexity is measures how hard it is to reproduce your system, so to obtain your system as an output of a Turing machine. This is a very deep concept in my humble opinion, and I've always been kind of fascinated by it. And the main reason why I am fascinated by it is that it's very hard, well, actually impossible to compute. But let's get back to it in a minute. So just to give, I'm pretty sure you are quite comfortable with this concept, but just to explain what I mean by description length, or better, by length of the best of the smallest program that can represent an object. Imagine that you have this object on the left, which is just a series of sequence of AB, and we can describe this object, obtain this object through different programs for humans in this case. So the program for a human could be write 18 times the string AB, which gives us output the stuff we have on the left, or we can have something like repeat AB 18 times, where 18 is written in Arab Arab numbers, and then we can have this description here, which is readable by anybody who is literate with regular expressions, and it says take a B, repeat it 9 times, and repeat the composition of these two for 18 times, which is exactly the same, which provides exactly the same input. So all these 3 programs provide the same stuff as output, but the shortest one would be the last one. So the last one, the length of the last one would be the Kolmogorov complexity of your stuff on the left. There is a minor caveat, as I said before, and the problem is that Kolmogorov complexity is not computable. There is a very nice proof that shows that you cannot actually compute the Kolmogorov complexity of any object, because if you could, then the complexity of your object would be smaller than the value you have just computed. It's very nice and very old proof. But anyway, Kolmogorov complexity is not computable. So what you do, you try to find some sort of sensible approximation for some definition, for some sensible definition of sensible, as I normally like to say. So there is one possible approach, which is consider your initial object that I will call M, and you compress this object or the string that represents the bit string that represents this object with any compression algorithm that you want, and you then say that an upper bound for the Kolmogorov complexity of M is the concatenation of the output of your compression algorithm plus the compression algorithm itself. Because if you use these two things, so the compression algorithm plus the output of the compression algorithm on the original object, you could ideally run this stuff on a Turing machine and obtain back your object. So the size of this concatenation would be the size of your an upper bound for the Kolmogorov complexity of M. It's just an upper bound, obviously, so it's not, you don't know whether this is a good bound at all.
So one thing that I never understood about this approximation is the following, and no one ever gave me a good answer, but maybe. So since even the previous, the previous proof, the proof of non-computability of Kolmogorov.
Oh, I didn't provide it. Okay, so
yeah. So that is in essence a proof, by by absurd. Right, but this one you can also find the same fallacy, right? Because if I give you, when you combine in essence the coding of the compressed coding of the original entity plus the compressor itself, right?
Yes.
One could argue that you could find either a compression algorithm whose coding is shorter, given the same output, meaning it's just a more effective compression algorithm, or a compression algorithm whose coding is bigger, let's say is a more complex compression algorithm, but whose output, the encoding of the original entity, is shorter, right? So in some sense, you have the same paradox here, which is if there was a representation of compressed structure plus compression algorithm that was of a given length, you could find a shorter compression by finding either a shorter compression algorithms or a more efficient one, right? So what is the catch here?
Yeah, the catch is that if you use the same stuff consistently, and you also compare different compression algorithms when you do that, then you should get a reasonable set of answers. What I mean is, if you have 10 systems of which you would like to compute an approximation of the Kolmogorov complexity, and you use the same procedure with four different compression algorithms, then the ranking of the relative complexities you get in each of the four algorithms should be preserved. And if that is preserved, it means that you are basically computing a sensible approximation with any of the algorithms you are using. You are in trouble if one of the algorithms gives totally different results.
So would it be fair to say that even a sensible approximation is almost, in essence, an empirical process? That
it is definitely an empirical process. As empirical,
not a theorem that proves that a sensible approximation is as good as.
In fact, I said the sensible for some definition of sensible. And the definition of sensible I have in mind is that you should get reasonably stable results across different possible implementation of the implementation details. So if you change the compression algorithm, or if you change something other, some other parameter that we'll talk about in a couple of minutes, then you should get something that is really robust enough.
But
okay.
Okay.
I also have a question before we move on, which is the one of the reasons why I emailed you. For anyone who's curious, I saw a really interesting PR Physical Review X paper, and I thought, you know what, this is interesting for me to discuss. So as you might not know, I was a postdoc at UC Davis, and I interacted a lot with Jim Crutchfield, and his I guess the most polite way to say it is his competitor I knew of but never met in person, Cosmo Shalisi. I like them both, and they both were in some sense critical of GZIP because, as Jim Crutchfield would say, causal entropy, a way of interpreting strings or a series of states with what's called an epsilon machine, could present a better bound than GZIP. So I guess two questions are, how much better a bound, or how bad a bound is GZIP typically? And also, is there some sort of causal entropy equivalent for networks?
These are two very nice questions, and the thing is, for the first question, I don't have a reasonable answer, and the only reasonable answer is that you can, and as we did, try different compression algorithms, and you can satisfy yourself in knowing, you can remain satisfied in knowing that you would not be able to find a proper a good bound, or even to estimate how good your bound is, but you could still be able to compare the relative complexity of different systems in a robust way. And this for the problem we have set up, which is comparing different systems in terms of their estimated complexity, could be enough. For the second thing, in terms of causal entropy, that's a much tougher question, I guess, because we should find a way of defining the causal entropy of a graph, which is not something immediate, I guess. There are a few possible ways of defining it, either in terms of the best matchings minimal model, which could actually produce a graph, but there are several caveats there, or in terms of the a suitable way of representing your graph as a causal algorithm. I don't know whether you have any good suggestions in that direction, but I would be very glad to explore these stuff, because to me, up to now, there is no really easy way of doing that. I really would like to be able to do that, because I know that causal entropy in several ways is a good way of quantifying how non-trivial an object is. Does it make any sense?
Yes, it does, actually. Thank you.
Yes, but I would be glad to actually continue this discussion offline if you like, because it's really something that is troubling me a lot.
Of course. Thank you.
Okay. Any more questions? Okay. So let's keep going. So what's the bottom line? So we have this complex object. If we want to compute the Kolmogorov complexity of this complex object, we have to provide a binary description. A binary is a bit string description of this object. Imagine that this is the binary description of this object. Then you use this machinery to get some sort of upper bound for the Kolmogorov complexity, and you don't know how good this bound is, as we have asserted. ascertained right now. But I'll give you a simple example here, just to give you a sense of which kind of results a Kolmogorov complexity can provide. And I consider a simple object, which is a book of about 12 megabits in words, in characters. And if you compute the Kolmogorov complexity of this book with this procedure, you get something that is about 3.7 megabits. So the length of the compressed stuff is about 3.7 megabits. If instead take a random sequence of A and B of the same length, so 12 megabits of A and B just put there at random, then you get something that is 1.8 megabits, which signals the fact that a random sequence of A and B is somehow less complex than a sequence of characters that reads into something that should be reasonable for humans. And then if you take something like AB repeated for 12 megabits, you get something that is instead 23 kilobits. So this bit string represents something that is very simple, but not as simple as a sequence of A, which boils down to just 11 kilobits, which is basically 2 orders of magnitude less than the original one. This can be read in this way, or this can be read in the other way, saying that basically these kind of books are more gibberish than a random sequence of A and B. It's as you like. But the thing is that the bottom line is that there is something captured by this Kolmogorov complexity. Now we have a problem. We have to represent a multiplex as a number, which is not something that is straightforward. So how do we get this number in order to be able to compute the Kolmogorov complexity of this object? And if we can do that, we can actually compare two multiplex by comparing the values of their Kolmogorov complexities. That's what this stuff is all about. Okay, so how do we decide to encode the multiplex into a bit string? We decide to associate a distinct prime number p alpha to each of the layers, and for each pair of nodes, so for each pair of nodes I and j, we computed the quantity omega ij, which is the product of all the prime numbers corresponding to the layers where these two nodes have an edge. So I'm basically representing all the edges between two nodes with the composite number obtained by the product of the distinct primes associated to each of the corresponding layers. And then we save the weighted edge list as a binary, a lexicographically sorted edge list as a binary, as a bit string. And notice that this representation does not lose any information about the original system. So it's a perfectly lossless representation of your original system, because you could always get back to the original graph by factoring the prime numbers that you have written down. Okay. There are some caveats here, so if you want, we can discuss it later. We do this for a system, and we obtain a bit string. So in principle, we can obtain the Kolmogorov complexity of this bit string. But the thing is that we don't want just a Kolmogorov complexity of your system as a multiplex, but we want to see how much this system differs from the single layer equivalent that you can obtain by flattening everything in a single graph. So what we did was to define the complexity of a multiplex as the ratio between the Kolmogorov complexity of the encoded multiplex, so the original data set you have, and the Kolmogorov complexity of the encoded aggregated graph that is associated to that data set. The larger this quantity, so this quantity is normally larger than 1, because if you have more layers, you will have more primes in your encoding, and you will have longer strings. And the larger this quantity, the more is the information the relative information contained in a multi-layer version of your system. And this is a simple example we did, a simple test we did. So we considered a certain number with a certain number m, with m varying between 4 and 60 of layers. So system with a synthetic, certain number of synthetic layers. And we started from m identical layers on the right, so that you have an edge overlap equal to 1, meaning that all the layers are the same. You have all the edges there. And obviously the Kolmogorov complexity in this case is always, the complexity of your system in this case is always 1, because you gain nothing into representing a system as 10 times or m times the symbols you need to represent it with just one set of symbols. Okay, it's all identical layers. And now what we did was to rewire the edges of these graphs in order to obtain a system that has less and less edge overlap, up to the point that when the edge overlap is 0, these networks have nothing in common anymore. So they are just the layers are just distinct layers, as if they were taken from completely different models. And what happens is that obviously at the left hand you have, at the right hand you have complexity equal to 1. But what happens is that the complexity is a non-monotonic function of edge overlap, meaning that there is a certain interval between 0.2 and 0.4 in this case. I think this is we have several models. This is a scale-free graph, I guess, for which you have a maximum amount of complexity, which is the maximum possible amount of differential information that the multi-layer system provides with respect to the single layer graph. And interestingly, this amount is comparable with the amount of edge overlap we observe in many real-world systems. So it looks like many real-world systems tend to put themselves in a region where the complexity of the corresponding multi-layer structural representation has maximum, is maximum, or is as close as possible to the maximum. And then we did some other tests for systems with different degree, and still you get something that has the same kind of non-monotonic behavior, and which has a minimum at 1. So this is really 1. And then you have the problem of actually comparing systems with a different number of links. Why is that? If you are familiar with the Kolmogorov complexity, you know that it depends logarithmically on the size of the string. So the Kolmogorov complexity cannot be smaller than a certain constant times the logarithm of the size of your string, just because you need at least that certain number of bits to produce that output. So basically, we use the normalized version of this complexity, which takes into account the fact that in different systems you can have different number of links in total, which contribute to the length of the string, because the length of the string is a function of the number of links you have in your system. And what we did was consider other interesting examples. So in the top panel, you have 10 distinct layers. And the maximum of this quantity is obviously when you consider all the 10 identical layers, sorry. And the maximum of this quantity is normally when you consider all the layers flattened together. Then we have 5 groups of 2 layers in the bottom panel. And the maximum of this quantity of this quality function is when the 5 groups are recognized. So when you have 2 layers in each of the corresponding 5 layers each coming from the flattening toward the original layers. And then we did something like different combinations of distinct layers and layers which are in different size groups of different sizes. And in all the cases, we actually obtained the desired partition. So the system is just aggregating up to a point where aggregating more will destroy some of the original information that's there. We did this in a more slightly more sophisticated way by by considering large-scale synthetic multiplex networks and real-world multiplex networks. And we looked at how much the structure of the reduced system. So on the x-axis, you have the number of layers. So when you go from 10 to 1 layer, you are actually aggregating. We looked at the correlation between the ranking of different structural properties with a certain number of layers and the same property on the original multi-layer graph. So we would like to preserve as much information about the original system, but using a smaller number of layers. And here we show the correlation for degree, BI is the activity, PI is the participation coefficient, and lambda I is the, I think at the end, this is the, how is it called? Maximal entropy rate. It's the maximum eigenvalue of the adjacency matrix. And you see that the gray dash dash and dot line always always cuts, which is the maximal corresponding, the multiplex corresponding to the optimal complexity, always get to the point where aggregates to the point where you have not lost information. After that point, you start losing structural information about your system. And not only that, but also you have the same for dynamical properties of your system. In this case, is not the percolation threshold, but is the epidemic threshold, which is the amount of disruption you have to create in your graph in order. Is the amount of is the efficiency of your system in terms of spreading. Okay, while the percolation threshold is the amount of damage you have to provide in your graph in order to destroy it. And basically, again, the Kolmogorov complexity is able to detect the point which preserves the epidemic threshold best, and after that point, the epidemic threshold changes dramatically. So basically, this quantity is able to preserve not just structural but also dynamical properties of your system. And then we go to close. We also use this information to track the evolution of complexity of different systems. On top left panel, you have the network of movie actor collaborations. Top right, you have financial systems between 1998 and 2014. You see that the maxima here of complexity correspond to the periods of maximum crisis. Local maxima are maximum crisis. Then bottom left, you have other collaboration networks, Web of Science and APS multiplex collaboration networks. And on the right bottom panel, you have the complexity of the FAO trade network, international trade network, which has increased in the last 30 or 40 years as a result of the globalization of food import-export across the world. Finally, we could also use these as a way of distinguish different kinds of networks when used together with some structural descriptor. This is the maximal entropy rate of the corresponding graph. Take-home message. The take-home message is that more data is not always a bliss, and this is something that is very important to stress. So if you have more data set, doesn't mean that you have got more information about your system. It just means that you have potentially more information about your system, but you should be able to unravel this information in a meaningful way in order to learn something more about your system. And luckily, information theory and complexity theory is here to help, meaning that by using information theory principles, we could actually unravel some of these information from bare data and decide whether we actually need all these data or not, because we have seen several examples where the single layer representation is actually the best. So even if you have 10 different dimensions, the information provided by the 10 different dimensions is not worth the effort, and a single layer or two-layer representation could provide exactly the same amount of information, structural and dynamical information of your system, but with a much smaller amount of data to retain. And then the third take-home message is that I think we have just scratched the surface here. So to paraphrase a very famous saying, that there is more room at the bottom, meaning that there is lots and lots of different things we have not yet understood about these multi-layer structures. And information theory is definitely, in my opinion, the way to go. So we need principled approaches in order to get something useful out of these data, especially because it tends to be too much data, and too much data is normally too much noise, too much false positive, too much of other undesirable drawbacks. Okay, so these are the two references. So the first part of the talk was about this paper on structural reducibility of multiplex networks I did with Manlio, Alex, and Vito back in 2015. And the second part, instead of algorithmic complexity, is this paper on FISBREVX that just went out in April 2020 with Andrea Santoro. And I must acknowledge my group. So Andrea Santoro is the person who is the first author on the PRX paper, on the Kolmogorov Complexity paper. And then Sandro and Silvia are two other PhD students. Andrea just finished this PhD and he will defend, hopefully, within a couple of months. Sandro and Silvia are still working at their PhD, and Aleix Bassolas is instead the PDRA. Working in my group since last February. A bit of advertisement. We are organizing a satellite of the Conference of Complex System 2020, and it's a satellite of complexity in spatial systems. So it's all about trying to understand complexity, how spatial constraints affect the complexity of a system. So if you have anything interesting to say, just please send an abstract. The submission is due by 11th of November, which is next week. And I think that's basically it. Thank you very much.
Great. Thank you so much, Vincenzo. One thing that surprises me about this work is when I was looking at it, I was thinking naively that it's always so easy to compress many layers of a multiplex network into a single layer. I didn't think too much about whether there is such an advantage to these multiple layers. Well, I know there are other researchers who would argue quite the opposite, that any compression is not needed. I was talking to a guy, UC Davis, in fact, who was very much in that perspective. So in some ways, I think this is very important because it helps give clarity to really how to represent a network system. And for that, I really want to thank you.
Thank you.
And in the meantime, I'm wondering if there are any other questions from people.
So I have one question or comment, I guess.
Please go.
So I agree. I mean, first of all, I have some, misgivings about the need for measuring complexity, or, but that's a philosophical conversation, better to be at, over wine or beer.
Yep, definitely.
So,
I can grab a beer if you want. Just need to go downstairs.
Well, it's still noon here, so
yeah.
But what I was going to say is that I agree with that. Information theory provides a nice tools to basically study this type of system. But when I say information theory, and we look at the Shannon's work, so the most important concept there is the concept of mutual information. Noisy channel. While most of the works that I've seen on graphs are basically talking about entropy, or one Newman entropy that you mentioned. So do you know any works that actually looks at the mutual information, let's say between different layers, rather than just calculating the
okay, not directly at mutual information between different layers. There is a work by Filippo Radicchi who has looked at the problem of information encoding as a mutual information problem, so noisy channel problem and identification problem, if you want. So getting encoding a graph in such a way that it could be obtained back as if it had passed through a noisy channel, okay, which is exactly what you are talking about. But that was just for single layer, mainly for single layer graphs. And my idea is that indeed something similar could be done for multi-layer graphs. And but I mean, I would be really interested to look into that problem of mutual information in this sense.
Right, and there is I know there is work on that in that area from the machine learning and computer science communities.
Yes.
Like there is this guy Emmanuel Abbe from Princeton.
Yes.
So they study basically networks as kind of noisy channels.
Yes.
And I'm going to post, just for your information, a recent preprint on
Please
information bottleneck model from machine learning applied to networks. So that might be useful as well.
Very good. And also there is another interesting pathway that is, for instance, the use of transfer entropy among layers, which is something we have actually tried. There's something that is kind of sleeping in a corner, but it's something that I really would like to get back to, because the concept of transfer entropy is somehow relevant from a dynamical point of view. So imagine that you're measuring how much a layer is necessary to understand another layer.
Right. Yeah, transfer entropy is a conditional mutual information. So that should
in practice we call transfer entropy what is conditional mutual information. But I mean, it's very interesting from a principle point of view, because you are really asking yourself how much you need a certain layer to describe another layer, which is exactly the point of understanding whether the two layers are related in any sensible way or not. So there is definitely different. I say that. I mean, it's just the beginning. There are several different things that we can do, and we should do that, because I don't believe that having more data is always a bliss. So yeah, definitely different pathways there.
Thank you, and thanks for the interesting talk.
Thank you very much.
Absolutely, and I also want to add on to that what Aram was saying. I don't know if you're aware of anyway, Jim Crutchfield and one of his postdocs, whose name I've just forgot, was actually very interested in transfer entropy, and in his own work, he was finding that there are limitations to what transfer entropy can give you. He made a paper in Physical Review Letters called "Information Flows?" And in that he showed counterexamples of where you could have multiple noisy channels, and that even if it would say that the transfer entropy was 0, it's actually trivial that if you knew 2 channels, you would immediately know the third. And thus suggesting, I don't know if maybe I'm just repeating what you already know.
No worries. Go on.
Well, so it also makes me wonder if maybe that would be critical if you were to try to use transfer entropy for network layers. Maybe between 2 network layers, that's perfectly fine. But once you get to 3 or more, maybe the complex relationships between multiple layers might make transfer entropy give you one solution, and care about multi-adic interactions giving you another solution. Would that be reasonable to think?
Yeah, and I wouldn't be surprised, because, for instance, we still have not solved the problem of defining mutual information for triadic relations, right? So I wouldn't be surprised to see some odd things coming up as soon as you move from dyadic relations to multiadic relations, for the simple reasons that it's not anymore, as we know, for the problem of mutual information, or 3-body or 4-body mutual information. It's not anymore a matter of just comparing the ways in which you can combine 2 objects, which is just one. It's a matter of understanding how the ensemble of all the possible combinations you can have contributes to the results that you want to get. And I wouldn't be surprised at all if moving to triadic relations would provide a quite complicated picture there. I think that we should definitely get there, but I'm not sure in whether one approach, either entropy, von Neumann entropy, mutual entropy, whatever, or transfer entropy is best. I think we should just try and see whether we find something that is reasonable. Also because it's not just a matter of encoding linear information. It's a matter of encoding some structure that is not linear anymore, and it's not easily embeddable in any you know, low dimensional space. And a network is very hard to actually cast into something that is low dimensional. So I wouldn't be surprised if transfer entropy wouldn't be able to easily disentangle the case of 3 layers providing exactly the same information, or 3 layers providing completely different information.
Yeah, thank you. Because actually, I should briefly mention, it's kind of reminds me of this work I've been doing related to AI fairness, where when people want to make artificial intelligence fair, there's many, over 20 definitions of fairness for AI. And I guess in some intuitive way, there's sort of, we know, just like we might know what is complex, or we might know what is a well-compressed network, the actual way to quantify that may be the open question for now.
Yeah, indeed.
But with that, I think it seems that, well, first off, I just want to double check if anyone has any other questions. Otherwise, I think we'll end this. Does anyone else here have any questions? All right. I should also mention that we have what's called an AID lunch, or we have a lunch right after where everyone at USC's Information Sciences Institute meet together and discuss. And it happens to be that we just happened to pick a time when that was happening right now. So if we end it a little early, then that's totally fine.
Okay. Cool.
All right, but thank you again for your talk. This was a very great talk.
Thank you very much.
No
and
problem.
Feel free to just you know, chip in and drop a line if you have any question or you would like to have a conversation. Please do. It would be a pleasure.
It's always a pleasure to talk.
Thanks.
Ciao Enzo, grazie, alla prossima.
Ciao Emilio, alla prossima, un abbraccio.
Bye.
Great, thank you much then.